Have you ever just stopped and wondered how scientists describe the incredible transformations happening all around us? From a mango slowly ripening on the counter to a fireworks exploding in a flash of light? Well, they use a universal language, kind of like a secret code, that precisely describes how all of that matter changes. Today, we're going to unlock that code together.
So, here's our game plan. We'll start with the very basics of describing a chemical change. Then we'll level up to using powerful symbols. We're going to cover the one fundamental law that governs absolutely everything, then learn the step-by-step method to get things balanced. After that, we'll see how to pack even more detail into our equations. And finally, we'll uncover the amazing predictive power this whole language gives us.
You and I, we see chemical changes literally everywhere. I mean, they are these fundamental processes where the very nature of a substance is permanently altered. But just seeing them isn't quite enough for science, right? We need a way to talk about them, to describe them with precision.
Just picture a mango ripening. The starches inside are converting to sugars, the color is changing from green to yellow, the texture is softening up. The original stuff is gone, and it's replaced by something totally new and, let's be honest, way more delicious. That is a chemical change in action. Or think about the total opposite, the flash and bang of a firework. It's a super fast, irreversible reaction where solids turn into light, heat, and gas in an instant. The original cracker, it's gone forever. Another perfect example of a chemical change.
So, how in the world do we get this down on paper? I mean, saying, I burned a firework and it went boom, isn't very scientific, is it? And writing out a long, wordy paragraph is just clumsy. We need a system.
And our first step is what's called a word equation. It's simple, it's clear. This one right here shows that calcium oxide, you might know it as quicklime, reacts with water to create a brand new substance, calcium hydroxide. That little arrow just means yields or produces.
All right, let's get a couple of key terms down. The things on the left side of the arrow, our starting ingredients, if you will, are called reactants. And the new substances on the right, what you end up with, those are the products. Reactants on the left, products on the right. Simple as that.
Now, word equations are a great start, but we can do better. We can make our language even more concise and way more powerful. So let's move on from just words to the actual chemical formulas of the things involved.
This right here, this is a skeleton equation. It just swaps the words for their chemical formulas. So CaO for calcium oxide, H2O for water, and CaOH2 for calcium hydroxide. Now, we don't just know what's reacting, but we know the exact ratio of atoms in each and every molecule. This is so much more informative.
But hold on a second. There's a problem here. Just because it's a skeleton equation doesn't mean it's right. Take this one, for example. Zinc plus hydrochloric acid yields zinc chloride plus hydrogen gas. Okay, let's do a quick head count. On the left, our reactants, we've got one zinc, one hydrogen, and one chlorine atom. Now look at the products on the right. We still have one zinc, but wait a minute. We suddenly have two hydrogen atoms and two chlorine atoms. Where did that extra hydrogen and chlorine come from? This equation is unbalanced, and that means it's breaking a fundamental rule of the universe.
And that rule is the law of conservation of mass. If we're thinking of chemical equations as a language, then this law is the most important rule of grammar. You absolutely cannot break it.
The law basically says that you can't create or destroy matter in a chemical reaction. You can't just magically create new atoms out of thin air, and you can't have them just vanish into nothing. The total amount of stuff you start with has to equal the total amount of stuff you end up with. So what that really means for us is this. For our equations to be correct, they have to reflect this law. And that translates into one simple actionable rule. The number of atoms for each element has to be exactly the same on both the reactant and the product side. They've got to match up. Okay, now we get to the really fun part, making our equations actually obey the law. Balancing is kind of like a logic puzzle. Now, we can't change the chemical formulas. Like, we can't change H2O to H3O, because that would change the actual substance. But we can change how many molecules are involved. Let's walk through it. All right, let's break this down in detail with the combustion of propane. First up, let's look at the carbon. We have 3 carbons on the left, so we need 3 on the right. Simple enough. We do that by putting a big 3 in front of the CO2. Done. Next, hydrogen. We've got 8 on the left, but only 2 on the right.
So to get to 8, we need to put a 4 in front of the H2O because 4 times 2 is 8. Okay, now for the tricky part, oxygen. Let's count up the oxygen on the right side now. In the 3CO2, we have 3 times 2, that's 6 oxygens. And in the 4H2O, we have 4 times 1, that's 4 oxygens. So 6 plus 4 is a total of 10 oxygen atoms on the right. To get 10 on the left, we just need to put a 5 in front of the O2 because 5 times 2 is 10. Let's do a final check. 3 carbons, 8 hydrogens, 10 oxygens on both sides. It's perfectly balanced. We did it!
We've balanced our equation. That is fantastic. But we can actually make it even better. We can add more little symbols to tell a much richer, more detailed story about what's really going on in the reaction.
We can specify the physical state of everything, an S for solid, L for liquid, and G for gas. We can even show if something's dissolved in water by writing AQ. We can show if heat is released or absorbed, if a gas bubbles up, or if a solid, we call that a precipitant, is formed. We can even write the specific conditions, like a certain temperature or a catalyst, right over the arrow. Each one of these symbols adds another layer to the story.
Let's see how this all comes together. Our balanced equation for iron oxide and aluminum now becomes a complete narrative. We can read this like a sentence. Solid iron oxide reacts with solid aluminum to produce solid iron and solid aluminum oxide. See? Every symbol tells us a crucial piece of information.
So we can now write and read the language of chemistry. But what's the ultimate point? Well, the real power of a balanced equation is its ability to make quantitative, real-world predictions.
The best way to think about a balanced equation is like it's a perfect chemical recipe. It tells you the exact ratio of ingredients you need and the exact amount of the final dish you're going to make. This whole field is called stoichiometry, and trust me, it's not just for the lab. It's the foundation for everything from making new medicines to manufacturing steel. It is incredibly powerful.
Let's put this to the test with our iron reaction. If we look up the atomic masses of the elements, our balanced equation tells us the exact mass ratio. For every 54 grams of aluminum we use, we get 112 grams of iron. Okay, so what if we're working in a factory and we need to produce 1,120 kilograms of iron? That ratio is always constant. So how much aluminum do we need to start with to hit our target? And the answer, using the ratio from our balanced equation, is exactly 540 kilograms of aluminum. No guesswork, no waste. That is the predictive power I'm talking about. It allows us to do these precise calculations that are just essential for all kinds of industries. And that brings us to one final thought. If a balanced equation really is a perfect recipe, what happens in the real world when you're baking a cake and you run out of flour, but you still have plenty of sugar and eggs? The whole process stops, right? Well, the exact same thing is true in chemistry, and that simple question opens up the next fascinating chapter of chemical reactions.